Okay, so for the honors pre-calculus final, I was assigned topic 6, problem C, and topic 6 investigates our ability to calculate the power of a complex number. And so the directions for this problem were to evaluate the expression and to leave your answer in a plus bi form. So problem 6, question C itself looks like this. So in parentheses we have negative 5 root 2 over 2 plus 5 root 2 over 2i, and parenthesis raised to the power of 9. So before I do anything else for this problem, what I'm going to do first is, since 5 root 2 over 2 isn't something that we recognize, and it's not something that we work with in pre-calculus, but when you take out that 5, you get root 2 over 2, which is something we do recognize and work with pretty often. So first I'm going to take out that 5. When we do something like that, when we're taking out the 5 of this problem, we'll do it like this when we factor out the 5. So we'll do 5 and then negative root 2 over 2 plus root 2 over 2, and parenthesis raised to the 9th power. So when we factor out the 5 from the original equation, it's going to look like this. And we know it's going to look like this because when you multiply a whole number by a fraction, you multiply from top to top and bottom to bottom. And since 5 is really equivalent to 5 over 1, when you multiply, you get 5x over y. So that's just a little explanation on how I factored out the 5 from this original problem. Now that we've gotten it into numbers that we recognize, negative root 2 over 2 and root 2 over 2i, and we factored out that 5, I decided that I was going to use Euler's formula to solve this problem. So this is what Euler's formula looks like right here. We have Euler's number raised to the power of I times theta, which gives us cosine theta plus I sine theta. And so having our original problem next to Euler's formula, it's pretty obvious that it is not in the correct form. So before we go any further with this problem, I'm going to convert these numbers that were in the given expression to polar form so that we can apply Euler's formula. The expression is given to us in rectangular form, and rectangular form is z equals a plus bi, but to use Euler's formula, we want to change this to polar form, which is equivalent to z equals cosine of theta plus sine of theta. So when we take rectangular form and transfer it to polar form, we aren't given a theta in this problem, but to transform into polar form, we know that these two values, this value and this value, are going to equal the cosine and sine value of a respective value that we can find on our unit circle. So as you can see, I have my unit circle right here, and in order to transform the given expression from rectangular form into polar form, we're going to find the coordinates on our unit circle that match up to what we're given in the expression. So now that we've simplified the expression and factored out the 5, we're given negative root 2 over 2 and root 2 over 2. And then to match those up to polar form, we know that this is going to be a cosine value and this is going to be a sine value, because as we learned earlier in the year, x is equivalent to cosine and y is equivalent to sine. So now that we have all that information, we're going to look for the value on the unit circle that has an x or cosine value of negative root 2 over 2 and a y or sine value of root 2 over 2. So just being familiar with our unit circle, we know that that value is going to be 3 pi over 4. So now that we've found the corresponding value on our unit circle, we can rewrite this as cosine 3 pi over 4 plus I sine 3 pi over 4. And I just moved the I from this side of the value to this side right in front of the I, just so it corresponds more exactly with polar form. And then I forgot right here but we still have to raise this 5 to the 9th power like I mentioned earlier. So I've rewritten it right here. And then we have to remember everything in this parenthesis right here is raised to the 9th power. So now it's time to plug these values into Euler's formula. So I have Euler's formula right here, and what I'm going to do is take Euler's number, and we're going to raise that to, first we have I, and then we're going to multiply that by 3 pi over 4, and then we're going to multiply that by the value that this whole expression is being raised to, which is 9. And so from Algebra 1, we know that when we have a number raised to a power within parentheses, and that's raised to another number, that this number in here is going to be equivalent to the product of those two numbers. So we can use that to solve this expression. And so as you can see here, I've just rewritten this a little bigger, but of course we're going to multiply it by I at the end, and it's all part of Euler's number is raised to this value times I. And so what we get is 3 pi over 4 times 9 over 1. And when we multiply these, we're multiplying straight across, just like we did in the beginning when we factored out the 5. So we do 3 pi times 9 is equal to 27 pi over 4 times 1, which is just equal to 4. And now that we have found the product that we got in the last step, we can rewrite the expression as 5 to the 9th power times cosine 27 pi over 4 plus I sine 27 pi over 4. And then we don't need that 9 that was on the outside of this parenthesis before because we multiplied it in to the theta value. And this can also be, you can also simplify this number, which you get a really big number. So I just left it as 5 to the 9th power. So we have this value, and we can see right here that it does match up to polar form, but the question asks us to leave our answer in a plus bi form. So I'm going to put it back into that form, which is rectangular form. So when we're converting this back to rectangular form, this is a really big number. So what I did is I put it into the form of a mixed number just to make it a little bit more manageable. And so 27 pi over 4 in the form of a mixed number is 6 3/4 pi. And so where we're going to go from here is we're going to take 6 3/4 pi and subtract the largest possible multiple of 2 pi. And so since we have 6, in this case, we're going to have k equal to 3, because if k is 3, 2 times 3 is 6, and then we get 6 pi. So 6 3/4 pi minus 6 pi gives us 3/4 pi. Just to explain this part a little bit more in depth, the reason that we use 2k pi, where k can be any integer, is because when we take our unit circle, we look and we know that one full time around the unit circle is equivalent to 2 pi. So when we take the value that we got, which would be 6 3/4 pi, we go around 3 times, which puts us right back at 3 pi over 4. And it goes around 3 times because 3 is the value that we selected for k, because 2 times 3 is 6, and that is the largest possible number that we could have taken out of 6 3/4 pi. So now that we have our new value, which is 3 pi over 4, we're going to look at our unit circle again, and as you can see, that's the same value as we started with, 3 pi over 4. And so this may seem a little bit overly convoluted and like a lot of work just to get the same number that we started with, but it really was necessary because we had to raise the numbers that we were given when we started with to the 9th power. And it just so happened that it was the same, that the product was the same value as we got when we started. So back to our binder paper, we still have 5 raised to the 9th power. We know that cosine 27 pi is the same thing as 6 3/4 pi plus I sine 6 3/4 pi. And after we did all those calculations on the whiteboard and looked at our unit circle, we know that these two values are, just like they were in the beginning, negative root 2 over 2 plus root 2 over 2. And I'll put I here just so it stays in that a plus bi form. And then we still have that 5, 9 at the front of the parentheses. So here I have our final answer, which is boxed up and put into the form that the problem asks for, which is a plus bi form. So we have 5 raised to the 9th, parenthesis, negative root 2 over 2 plus root 2 over 2i, parenthesis, or, and this is just the number 5 to the 9th power simplified, 1,953,125, parenthesis, negative root 2 over 2 plus root 2 over 2i, end parenthesis. And so that is it. Thank you so much for everything this year, Miss Yang. You really made learning math enjoyable, which is something that I didn't ever think could be possible. And you really gave me a lot of confidence in my math skills. So I can't ever thank you enough. Thank you so much. I hope you have a great summer. Bye-bye.